in an experiment.
And we don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This time, with COP28 looming, is it too late to limit climate change to 1.5 degrees?
And some plasma generating hairy fibres. I'm Shamini Bundell.
And I'm Nick Petrichow. The UN's Climate Change Conference, COP28, is starting in a few days. World leaders, scientists, and various movers and shakers in all things climate will descend on Dubai. To find out what to expect, I'm joined by Jeff Tollison, who covers climate change here at Nature. Jeff, how's it going?
Good. Good to be here, Nick.
Well, thanks for joining me. Now, one of the big topics at this year's COP28, is the goal of keeping warming under 1.5 degrees. This was a key target of the 2015 Paris Agreement to avoid the worst impacts of climate change, and this particular COP will mark the end of the formal assessment of how it's going so far. You've written a feature about this topic, so to start with, let me ask, 8 years on from Paris, how big is this challenge?
Well, it's big, and it gets bigger every year. The short story is that emissions are still rising. And despite a lot of progress in terms of, renewable energy deployments and costs coming down for clean energy technology and lots of commitments, the simple fact is that emissions are at record levels, and we don't really have an easy pathway to cut emissions over the next, 12 years or so in order to easily meet that 1.5 degree target without extracting large amounts of CO2 later in the century.
And from your feature, it kind of seems like the language is changing a little bit from can we meet 1.5, but exactly what the overshoot will be. So can you tell me a little bit about that? What are scientists sort of predicting now as we go forward into the future?
Well, there are a lot of projections out there, and all of them rely on a lot of assumptions. So you have to take all of this with a grain of salt. But in general, the people who kind of track energy and climate policies and emissions estimate that, if the world were to kind of maintain its current level of momentum, you'd wind up somewhere around 2.5 degrees of warming by the end of the century. And that does represent progress. A decade ago, we were talking about, warming of well over 3 degrees. So business as usual has changed. That's the good news. But there's still a big yawning gap between 2.5, which is, our best estimate for where we're headed, and 1.5 or 2.
Now, with this sort of overshoot idea in mind, this relies on a lot of assumptions that will be able to pull a lot of CO2 out the atmosphere. Where is the science on that, and how likely is it that we're going to be able to pull a lot of CO2 out of the atmosphere later this century?
Well, that is the trillion-dollar question. Nobody really knows. There's a lot of R&D underway into various methodologies for extracting carbon. You can do it with industrial processes, perhaps. You might be able to do it with nature-based policies, extracting CO2 out of the atmosphere and into the ocean, planting forests. Some of these are pretty basic things that we know how to do, but in a lot of cases, the science just isn't there in terms of the, both how you accomplish these things at large scale and whether there might be unintended knock-on effects that occur when you deploy these things at large scale. So the real challenge here is that we've got a situation where the international political agreement that people are following is kind of guiding us in a way as to depend on negative emissions, on extracting CO2 out of the atmosphere later in the century. And we really don't have the technologies today that we know how to do that. So there's a lot of need for R&D, for investments, and for government policies that will start to ramp things up in case we do need these technologies in the years to come. That said, one thing is clear. The first thing that the world needs to do is stop emitting. And then we can think about how to run the climate in reverse and extract CO2.
And so looking forward to COP28, which is starting in a few days at the time of recording, what do we need to, I guess, try and keep this dream of 1.5 alive? What do we need to see coming out of this COP?
Well, this is the annual question. I mean, really what we need is more action at the national level and less talk at meetings like these. That said, these meetings do serve a very real purpose in terms of kind of setting international agendas and holding countries to account. So in theory, countries have already committed to do what needs to be done under Paris. But the reality is that everybody knew in 2015 that the commitments that have been made, were falling short of the goals that were laid out in that agreement. And so what was done to account for that fact was to set up this kind of global stocktake process. And the basic idea is that every 5 years, governments have to kind of look squarely at the numbers, do an assessment of their collective progress toward the Paris goals. And in theory, the results of that are supposed to inform the next round of commitments. How that is going to work, it's still a little bit unclear. What exactly needs to come out of COP28, it's still a little bit unclear. But people are talking about some landing spaces. There may be some new language kind of setting a path toward 1.5, again, laying out what needs to be done and then calling on countries to double down on their efforts. There are other things going on in the sidelines, which are focused on setting a global agreement on phasing out fossil fuels and ramping up climate finance. So there are many levers that you can attack this problem through: finance, fossil fuel commitments, renewable energy commitments. All of those things are going to be in play at COP28. We'll have to see how things play out then.
And speaking of the sort of like language of agreements, there has been a lot of talk about a sort of phase down of fossil fuels to meet our climate goals. We obviously need to stop using so many fossil fuels. And this year, the hosts are the United Arab Emirates, the UAE, and the UAE is a big fossil fuel exporter, as are many other countries, including the US. But are there any concerns here that there may be, some sense of conflict of interest?
Well, certainly. And there have been accusations raised that the UAE has used its presidency of the COP to actually push fossil fuels. I mean, if you step back, there's a dynamic within these negotiations that was always there. And the major fossil fuel producers, including the UAE and also the United States, Russia, a lot of Gulf Coast countries, all have a kind of collective interest in maintaining fossil fuel production. And this has always been a problem. One can expect them to argue against stringent language on a fossil fuel phase out. And so this is going to be the dynamic at COP28 on this key point. And I think we should note that this is one of the most fundamental points. The science is perfectly clear. The climate will keep warming as long as we're pumping emissions into the atmosphere. And that means the climate will keep warming as long as we're producing and using fossil fuels, at least without capturing those emissions and doing something else with them, like pumping them underground.
And speaking of emissions, the leaders of the two biggest carbon emitters, China and the US, are not in attendance this year. Does their absence put a bit of a dampener on people's expectations from this COP?
I would imagine it does, but we'll kind of have to see how things play out. At the same time, there was this kind of new deal announced between the US and China, which I think a lot of people in the international sphere think is a big deal. One might ask why. The US and China have worked together on these kinds of things in the past, and we are where we are, which is not where we need to be. So does it make a difference? Well, these things are hard to measure, but in terms of the way the negotiations work, the politics inside the COP, it is important to have the two world's largest emitters on board and talking to each other, which hasn't been the case in recent years due to disagreements on multiple fronts. So, The fact that they're not coming is not the best of news. The fact that they're working together is good news. Make of that what you will.
And so, how are you feeling going into this year's COP? Optimistic, pessimistic, or somewhere in between?
Certainly not optimistic. That said, it's becoming increasingly clear that the transition that we need is happening. The economic transition toward clean energy seems to be unstoppable at this point, and given time, that will change the politics, and that will drive new policies and new commitments. The problem is that we don't have a lot of time, and that's where the challenges come.
A tall order indeed. Well, Jeff, thank you so much for joining me.
You're welcome.
That was Jeff Tollefson. For more on Nature's climate coverage, check out the show notes for some links.
Coming up, an easier way to make plasma. Right now, though, it's the research highlights read by Dan Fox.
Crows and parrots may be known for their cleverness, but researchers have found wild falcons are no bird brains either. Researchers tested 15 striated caracaras, a species of falcon, for their ability to find new solutions to a problem. The birds were faced with 8 tasks to solve for a food reward, each with a different solution, such as sliding a door or pulling a wire. The team found that the birds worked out solutions at a rate as high as 1 per 1.6 minutes during their first attempt at the tasks, and during subsequent attempts solved more tasks and completed them faster. Eventually, one bird was able to complete all 8 in under 5 minutes. Nearly all caracaras completed all the tasks, including ones that had stumped more than 50% of Goffin's cockatoos, birds renowned for their problem solving. The authors say these falcons are a promising model for examining bird intelligence in the wild. The early bird catches that research in Current Biology. Smoke from the record-breaking 2020 wildfires in California contributed to cloudier days in Europe. Researchers used remote sensing technology to monitor the distribution of fine particles in the atmosphere above Cyprus in late October 2020. They found that smoke particles originating from wildfires burning in California earlier that month reached the eastern Mediterranean in 8 to 9 days. Above Cyprus, these particles triggered the formation of extended layers of long, wispy white cirrus clouds. The findings could have implications for the climate, given that clouds have a key role in regulating the amount of solar radiation trapped near the Earth's surface, and climate change means the frequency of wildfires is rising. Read that research in full in Atmospheric Chemistry and Physics.
Finally, it is briefing chat time here on the Nature Podcast, where we discuss some stories that have come up in the Nature Briefing. So, Nick, what's your pick for this week?
Well, I've been reading in Nature about the most powerful cosmic ray that's been spotted for about 30 years, and it has scientists kind of puzzled.
Ooh, well, we love puzzling signals from space here on the Nature Podcast. What is so puzzling about this particular cosmic ray?
Yeah, so this particular cosmic ray is very powerful, and that's what is puzzling scientists, because they don't really know how it's created or where it's coming from. And I should say as well, cosmic rays are kind of confusingly named. They're not really rays at all. They're particles. So they're often protons, but they're these particles that sort of zip through space at sort of a incredible speed, almost the speed of light often. And in this case, this particular particle that was spotted has an incredible amount of energy. So it had an amount of energy which is 240 electron volts, which is a unit of measurement which is like 10 to the 18. And one, it's a lot of energy.
Okay. Yeah, I was going to say, I don't know that one, the Exa. I know like giga, mega, but yeah, that's the 10 to the 18 is a pretty high one there.
Yeah, it's a pretty high one. So to put that into some amount of context, 1 electron volt is 1 million times what we can make with the most powerful particle accelerator. So the reason you probably haven't come across it is it's not something we get a whole lot. The other example of something that was in the electron volt range was the cosmic ray that was seen back in 1991, nicknamed the Oh My God particle, because it was around 320 electron volts, so even more powerful than this one that was just seen now.
And so cosmic rays in general, do we have any idea where any of them have come from? Like, do we know that they're all even the same thing? Is it just this one that's sort of doesn't fit?
So we don't exactly know where cosmic rays are coming from. We've got some ideas. Supernovas seem like quite a good candidate, but also cosmic rays seem to come from some regions of space more so than others, so there could be something special going on there. But the particularly confusing thing about this cosmic ray, which has been named Amaterasu after the Japanese Shinto goddess of the sun, is because it is so high energy, it shouldn't really be affected very much by magnetic fields. So it should travel through space in pretty much a straight line. And so therefore, you should be quite easily able to see where it's come from. But when researchers looked at this cosmic ray and tried to trace its path backwards, it seemed to be coming from just a void in space, which is kind of confusing. If it'd come from a black hole or a quasar or something, you might be like, oh, well, that's what's creating it. But in this case, it seems to have come from nowhere at all.
A mysterious void with mysterious rays. So presumably, despite the mystery and the puzzle, the scientists have their various theories?
They do have their theories, but the theories themselves are quite interesting. So I'll start with the more dull theory first. The dull theory is perhaps there is some sort of mistake or misunderstanding in how we understand magnetic fields and their interaction with these cosmic rays. It could be the course that we've traced back is leading us to the wrong place, not actually the source of this cosmic ray. The more interesting theory, though, is that this has been created by some sort of novel physics. And we know on the Nature podcast that physicists love a bit of new physics. So that is certainly more intriguing. But time will tell exactly what that would be.
Oh, so the theory is just new, something we don't understand yet. It's not even an actual explanation. It's just we don't have the understanding yet to be able to explain this.
Yeah, because we don't know how anything with this much energy could be created, how it's travelling so far, and, you know, if it's coming from a void, what's creating it in this void? So there's a lot of big questions to be had about this. And the other thing is that, as I say, there's just been these two cosmic rays with this incredible amount of energy, this Oh My God particle, and now this Amaterasu particle. So they're quite rare, so it's hard to sort of study exactly where it is they're coming from. But hopefully, in the future, we'll see more. The telescope array that spotted this particular cosmic ray are upgrading their equipment to be a lot more sensitive, so perhaps we can spot more like them in the future. Because they do sort of fall across the Earth, but Earth is quite a big place and they don't tend to have this high energy. So having a more sensitive array will be quite useful in spotting cosmic rays in the future.
Whichever theory is right, it's quite interesting that it just does highlight what we don't know, in this case, about whether it's space, magnetism, weird rays. Either way, yeah, more space mysteries incoming on the podcast for sure. Mine is not a space mystery for you today. I've also got a story today that's from a Nature paper, and I've been making a video on this, so that's why I've been already digging into this particular one. And it's about a new way of making plasma, so the state of matter known as plasma.
Amazing. New ways to make plasma. Sounds incredible. Just so we're on the same page, though, what is plasma when we're referring to it? You talked about like a different state of matter. What is it when something is plasma?
Plasma is both weirdly alien and kind of really common in that, on the one hand, plasma is when matter isn't a solid liquid or a gas. It can be a plasma, which is basically, it's kind of like a soup of charged particles. And on the one hand, this can happen in really exotic places like lightning strikes or like in the sun. But on the other hand, it can also be harnessed for like plasma TVs and like neon lights and things which have plasma inside them.
Okay, so it's got a lot of uses then, I guess. So why are researchers interested in finding sort of a new way to make it? What's wrong with the old methods?
Yeah, Yeah, so in a way, plasma, as it does exist in tubeless stuff, is not that hard to make. What you do is you get a gas, a neutral gas, and you apply, or this is one way, you can apply a really big voltage across it. And if you get a big enough voltage, the electrons detach from the atoms in the gas, and then you've got electrons, and then you've got ions, and then you've got all these charged particles sort of moving around, high energy, with this sort of current flowing across this voltage gap between two plates, say, or two tips of some sort of conducting material. And all of that movement basically emits heat and light. And depending on the conditions, that can be some really extreme light and heat. And that's the kind of use that would be like a plasma cutter, or like plasma arc welding, where they make this little arc of plasma inside the machine and then use that heat, that extreme heat. And that's what this particular research is on, finding a better way to make extreme heat. And what the difference is with sort of all these uses and sort of methods that have come before is what they wanted to do and have been able to do is create this really stable and uniform plasma. So rather than what's called an arc, so think like a lightning strike, sort of crossing that gap where it's kind of jumpy, it's not very stable, and it's only kind of between 2 points. What they want is a sort of a volume of gas that is all this plasma and is all of equal temperature, and you can use that in science experiments, in particular looking at high temperature materials, certain materials that are made at really high temperatures. And there's also the actual sort of manufacture of those high temperature materials as well. This is exactly the kind of thing that would be really useful for.
So how have they managed then to get this sort of more stable plasma?
So hairy blocks is the answer, excitingly. They've used hairy blocks. Yeah, no, it's true. Watch my video, you will see hairy blocks in action. It's basically, instead of using, say, tungsten tips, they use these carbon fibre blocks that are hairy. They look like, it looks hairy. It's all these little carbon fibre fibres, I suppose. And the reason it works is that each of the little hairs over this sort of flat surface acts as an individual tip to have this sort of voltage build up and this arc go across from one side to the other. And because you've got so many of them close together, they all just sort of merge together, and it becomes this, like, all of the gas in that space between those two hairy plates all turns into a plasma, and it's all mixing, and it's all sort of the same temperature and light. It's really bright, so they have to wear sunglasses. I've got some video clips of the researchers looking very cool in their special sunglasses, special lab sunglasses that basically stop them going blind while staring into the blinding light. And it's incredibly hot, and then that is a much more useful way to, let's say, make a material, because you've now got like a little area in which you can heat up a volume of material, say.
And the way you described it, it sounds very simple. Just, throw some hairy blocks in. But how straightforward? Easy. How straightforward would it be for people to use and maybe potentially put in their plasma cutters?
Well, so I was speaking to the researchers, and it sounds very high tech, and like these kind of plasma experiments, when people are doing experiments with these kind of like really high temperatures, like hotter than the surface of the sun type temperatures, a lot of the work on this is done in there's just a few specialist labs, like physics labs around the world, and you need all this special kit. But actually the researchers say, hey, you know what, this is really simple. All of the components that we've used are relatively easy to access, and they're really excited that actually any physics lab could recreate their setup and have access to this sort of super high temperature plasma to do experiments on. And yeah, they say it really opens the door for a lot more of this kind of work to be done in a lot easier way.
But yeah, that's in a lab setting. What about potential applications? Does this more stable form of plasma lend itself to any other sort of applications that people could use?
Yeah, so again, the researchers reckon they think their method is great. They think it could replace current manufacturing methods that are used to produce certain high temperature materials. The example that they gave was jet engine turbine blades, where they're going to be spinning round and round. They're going to be subject to these extreme heats, and you need a material that isn't going to kind of like melt and warp and sort of stretch as it's spinning and being heated. And therefore, what they use is these materials that are made, that are created at these high temperatures. And that was an example of something that could potentially be made with this method.
Well, it certainly sounds like it opens up a lot of potential. Thanks, Shamini. But I think that's all we've got time for on this week's briefing. Listeners, if you want to know more about any of the stories we discussed, there'll be links to them in the show notes, along with a link to Shamini's video, if you fancy seeing some plasma production in action.
That is not all from the Nature Podcast this week, though, because keep an eye on your podcast feed, and there's going to be another bit of podcast goodness coming up tomorrow. We've got a special one-off episode for you.
But for now, if you want to keep in touch with us, you can. We're on X at Nature Podcast, or you can email us podcast@nature.com. I'm Nick Petrichow.
And I'm Shamini Bundell. Thanks for listening.